Okay, questions about SN1s, SN2s?
Does chapter 8 do the problems?
I think so, but I could move it to Wednesday night too. Remember, there's the hard deadline is when I go in and I write down the scores. And I can tell you I haven't done that yet. So if you haven't gotten to chapter 7, the thing is I'd like all the chapter 8 problems to be due before the exam and not the day of the exam. So I can move those to Wednesday if you're a little bit behind. But that's after Wednesday I'll write down the scores. So it's a little self-paced that way, but that way you've got those problems before the exam. Let me make sure I've got that. Any other questions about stuff? So I rearranged the schedule. I rearranged the schedule. We'll start with E2 after this exam. The last thing though I want to talk about with SN1 is carbo-cation rearrangements, which is actually I think it's part of chapter 7. So we talked about this before, but then I kind of said, well, I'm just going to introduce it. And then we're going to go back and take a much deeper look at it when it's time. It's time. So what we mean by carbo-cation rearrangements is something like this. Let's say that we start with that reaction. Now, after we went through and developed the chart on Friday, can you tell me what kind of reaction this is? Oh, better yet, let's just start by having you type. So your choices are A, SN1, and B, SN2, and C, I guess C is going to be don't know. Remember, this is participation, so I just have to make sure I got the right class. So it's going to be A, is it SN1, B, is it SN2, or C, don't know. Given our table of results. it not have internet either? Okay. I've got you marked out, so. All right, let's see what people have. 24 A's and 4 B's. So why did you choose it being SN1? Water's a weak nucleophile, and that automatically makes it SN1. It's as good an answer as any. If you look at the chart, you could say, okay, it's SN. It's a secondary halide and a weak nucleophile. That's SN1 as well. So it's got to be SN1. Good. So hopefully you can use that chart without it being there, with it being up here on Friday. So it's going to be SN1. So what's going to be the first step in this mechanism? The first step is going to be to break the carbon-chlorine bond and form the secondary carbocation. And then the water is going to come in and add to that secondary carbocation. To form the oxonium ion. And then I'm going to lose H plus to give me my product. So that is how we would expect the reaction to go. And so the real surprise here in this reaction would be if you got another alcohol product. And that's what happens. I don't know if it happens 10% of the time, 20% of the time, 30% of the time, probably not 100% of the time. But there is the possibility of getting another alcohol, and that's going through a carbo-cation rearrangement. Okay. So when people were doing this reaction, they got multiple products, even if it was a small amount of this other product that I'm going to show you. Okay. So let's see what the carbo-cation rearrangement is. So what happens is that if you have this carbocation, this secondary carbocation, what can happen is that on the carbons next to the carbocation, if you can form a more stable carbocation by shifting a hydrogen or a methyl group, that can happen. And so what can happen is this hydrogen can move over, taking its pair of electrons. So it's moving as an H minus, which is what we would call a hydride. And I'll write the transition state here. The transition state would have the hydrogen partially bonded to both of the carbons. The hydrogen the carbon that it's moving from, and the carbon that it's moving to. And then each one of those carbons would then share a delta positive sign. So this is the transition state for that, what we're going to call a hydride shift or a carbocation rearrangement. So the hydrogen is like bridged between the two carbons. But the hydrogen's not big enough to just sit there. It's got to choose one. So it's going to slide over from one to the other. And what's then going to happen is that once it has completely moved, the plus charge then moves itself to the carbon on the left. What don't you like about that? You have this look like. Does that really happen? So that's what the hydride. This is called a 1,2 hydride shift. The same thing can happen for a methyl group. And this is also then called the carbo-cation rearrangement. So when you do this reaction, I'm assuming, with these carbo-cation rearrangements, I'm very skeptical of some of them. I'll show you one that I know happens because it happened. And I think I've used this example in the past. But if you get both products, then this was the proposed mechanism for these 1,2 shifts. And I think that's called a 1,2 Mervin-Pondorf shift or something like that. But what they did was they studied different shifts, different molecules to see when the shift would occur. And the driving force for this is always the formation of a more stable carbocation. That's always the driving force. So you can go from a secondary to a tertiary. You could go from a primary to either a secondary or a tertiary, and I'll show you how that happens in a minute. But the driving force is always the formation of the more stable carbocation. And the other issue with this is that there's no multiple steps. You get one shot. You get one rearrangement. You can't have the plus charge go down the line of carbons until it finds a good spot. Because this is a transition state. It costs energy. Right? So if I'm looking at this reaction, I went to form the transition state, which is the hydride shift, and then I'm forming my carbocation. And I actually went from carbocation to carbocation, so the way I drew that is not correct, because the carbocation that I formed was more stable than the one I started with. So what pays the price in that activation energy is going to be the formation of a more stable carbocation. So the rules are you can only have one shift. You only get one shift, and you have to form a more stable carbocation. And that's the thing about carbocation shifts. One of the problems with carbocation shifts.
Oh, is it more stable because it's on a tertiary?
Yes. So I went from a secondary carbocation now to a tertiary carbocation. So that's why it's more stable. the problem with these shifts is that once you see them, you're tempted to like do them all the time. And the people who write book problems, which isn't necessarily the case with the electronic book, but with the paper books, one author writes the book and another author writes the supplementary problem set. And so what happens is you see these just random shifts. And so you never know when to do them. I'll tell you when to do them. I usually put a little star on the problem and say, write the rearranged product. Or if I'm giving you a mechanism, it's clear that the product you're making has to undergo a shift for you to get there with the mechanism. So I always tell you when to do the shifts. Because it's not totally clear how much this occurs. And a lot of times the products that we get, you could get from more than one, so it's hard to say when you get the shift, when you don't get the shift. Okay. But they can occur, and they do occur. Whether they occur 100% of the time is going to be case by case. I'm not sure that I fully understand. And I haven't gone back to look at all the primary literature of how they came up with this, because that would have been in the 60s. Because carbocations were big in the 60s. And that's when everybody studied them. And then nobody's touched them since. So that's the driving force for this. But one of the things that I will say is that when you have this problem, the first step is to lose the leaving group and form the carbocation, and then shift. So if you can form a carbocation and then do the shift, that's what you want to do. Oftentimes on exams, what people will do is they'll shift the hydrogen and kick off the leaving group, which I'm going to do in a minute. But that can only occur when you can't form a stable carbocation. But in this case, we can form that secondary stable carbocation. Okay, so that's what you want to do in terms of the mechanism. Is form the secondary carbocation, and then if the product needs to be shifted, then you can go ahead and shift either a hydrogen or a methyl group. Okay. All right. So we had done this back in chapter, it's probably chapter 3, because they were talking about the one-step mechanism. And then they introduced the idea of these shifts. Okay. Right. So here's one that I know happened. And I probably told this story when we talked about it. And I can't remember if I talked about it in both classes or not. So one of the ways that you can make carbocations is to treat an alkyl chloride with aluminum trichloride. This is a reaction we'll do next semester. It's called a Friedel-Crafts Alkylation. And the result of this is a benzene ring. This reacts with a benzene ring. But I'm just going to show you how the carbocation is formed. So what the aluminum can do is the aluminum comes in and basically it grabs the chlorine, although that's not really the way it works. The chlorine breaks its bond and transfers its electrons to bond to the aluminum, because the aluminum-chlorine bond is pretty strong. So either way you want to look at it, the aluminum ripping the chlorine off or the chlorine just jumping off to join the aluminum, either way, that's what happens. Now, in this case, what would happen is I would be left with a primary carbocation, which I'm still not allowed to draw. So when you treat this molecule with aluminum chloride, or this happens with any primary alkyl halide, the hydrogen shifts over and the chlorine leaves. To avoid forming the primary carbocation. So the transition state of this would look something like this. There would be a partial bond to the chlorine, a partial bond to the hydrogen in the two places that it's going, and then actually a partial bond to the aluminum trichloride. And so in this transition state, and I'm not going to worry about the charges for this because we'll talk about that next semester, but ultimately what I end up with is this. And then the chloride goes over to form AlCl4. So I know this shift happens. And again, you're going to have the movement of the hydrogen and the leaving group leaving only in the case of primaries. That's the only time you're going to have the hydrogen shift and the leaving group leave. If it's a secondary carbon, then you're going to form the carbocation first and then have it react, then have the shift occur. So this reaction, when I taught organic lab at OU for my one glorious year there, what I wanted to do was they were supposed to react tertiary butyl chloride with aluminum trichloride to make a tertiary butyl carbocation, which would then add to a benzene ring. And about halfway through the lab, some astute young scholar said, because they're all scholars down there, said, oh, we're using isobutyl chloride instead of tertiary butyl chloride, because apparently I had pulled the wrong one from the shelf. And so then I looked and I said, that's okay, it'll work anyway. And then they kind of were like, are you sure? I'm like, I'm in charge. Shouldn't I be in sure? Right? You asked me in lab, are you sure? Like, if I'm not sure, then no one else in the lab is sure. So I said, yeah, and I said, that'd make a really good post-lab question, right? The mechanism of how we're going to get the same product. And this is the mechanism. So I know in that case it made the tertiary butyl carbocation, because that's what it did. So some of these are a lock. It'll form it 100% of the time. Other ones I'm just not quite sure of. So when you see these in the book on a piece of paper, it's interesting that what we write may only occur 5 or 10% of the time in real life. And I think and one of the students is kind of working to see if there's some cases where we could actually pin that down and say, oh, this is like 50-50, or this gives what we write on, this doesn't give what we write on paper, it gives something else. So there are a lot of complexities to this, but when we're talking about hydride shifts or carbo-cation rearrangements, they fall into two classes. Either you form the carbocation first, then shift, or you move the hydride and then with the leaving group. Okay. You could also do this same reaction and shift a methyl group as well. So another reaction that's possible is to take this one and react it with H2O with a touch of heat. And you would look at this reaction and you'd say, well, that's a no reaction. Right? Because it's a primary plus a neutral nucleophile. Well, if I heat this reaction up, I could get it to go, because what would happen in this case is before the water added, I could do a methyl shift, which is perfectly allowed, where the methyl would shift over as its pair of electrons, and then it would kick off the chlorine, so that that transition state would have the methyl group now partially bonded between the two carbons, a partial bond to the chlorine, and so the transition state would look like that. In this one, we can put the charges in, because then the final product would be the chloride ion and the tertiary pentyl carbocation. So the delta plus would go on this carbon. There'd be a small delta plus here and a delta minus on the chlorine. And you could question whether or not the delta plus is going to be on that CH2. There's not going to be very much because it's primary, and the bulk of it's going to be to the tertiary carbocation. So you can shift both methyl groups and hydrogens. But the result is always the formation of a more stable carbocation. And just to make this reaction a little more realistic, I probably would apply a little bit of heat. I would also include some silver ion, because we know that silver likes to precipitate with chlorine. So if you added a little bit of silver to this, the silver would also help pull off the chlorine, or once the chlorine is done, would immediately react with it and precipitate out of solution. A lot of times that's how we can tell if we want to do visual tests to determine if an SN1 reaction occurs. If we add a little bit of silver to the solution, if we see a precipitate, we know we formed a carbocation, because that's the only way the chloride immediately, if we see it immediately, then we know it's an SN1 reaction, because SN2s require some heat. Right, so that's the whole idea of carbocation rearrangements. Is everybody kind of with me? So, what would be the rearranged product of this reaction? see, how much success have we had with the drawing of products? So I want to know what the major product of that reaction was rearranged. So let me go to chapter 7 here. And let me create a discussion question. And allow students to draw. Okay. Let's see if you can draw the major rearranged product. Did it come out? Oh. I thought I eliminated I thought I got rid of that. Hold on one second. Alright, has that gone away? Or is it still requiring you to do attendance? Still says attendance. Let's see, I'm not even in the right class. Okay. I thought it just told you to push the button if you wanted to take attendance. Now what's it doing? Is it asking for attendance? Is it asking for a code? Somebody, wait, are you just typing in a code? Is it 3446? We'll clear this away and then I can... 3446 is your attendance code. See, this is how they take attendance at big universities where they're teaching in one and double-decker lecture labs or lecture halls. And then people give other people their phones, and so somebody's sitting there with 5 phones logging in 5 of their friends. It's been a long time since I've done that. Although I know at Ohio State they have their organic is double-decker lecture hall, because one of my former students is actually in charge of all the organic stuff. Shannon.
That problem's not showing up.
I know, because the problem is in the wrong class. So let me move it to the right class. You know, just give me a structure. So that we can vote on it. I'll give you 2. I'll give you more than 2. Bless you. Okay, there's 4 possible answers for the product of this reaction, for the rearranged product of this reaction. So my question is, which one of those is the rearranged product? And I'm going to go back here and make this a multiple choice. Okay. Bless you. So which one of those, A, B, C, or D, is the major, or is the structure of the rearranged product? Is that everybody? Everybody's input and answer? Anybody hasn't? So we got A, B, and C as our answers. Let's discuss for a minute. Since we have such a wide range of answers, let's discuss for a minute with somebody near you, and then we'll re-vote. Okay? The quieting down means it's time to vote again. So which one of these is the major rearranged product? Okay. So the beak became even more. Okay. So What's going to happen in the mechanism? I'm going to lose my chlorine to form that secondary carbocation. Now I'm going to look at the two carbons next to it, and there are two hydrogens. Hydrogen A, hydrogen B. Which one is going to shift? If there's going to be a shift, which one is going to be? HA or HB? Can we just yell a letter? All right, on the count of 3. I hear more A's than B's. So if A shifts, what do I end up with? I end up with the tertiary carbocation, whereas if B shifts, I end up with what kind of carbocation? Secondary. So again, the driving force is to form the more stable carbocation, so that will be the carbocation that it forms after shifting, and then the water will add to that, lose an H plus to give me the OH. So the correct answer here is B. Okay. Now I think in chapter 7, where this is at, or chapter 8, I think it's 8. Right, 9 will not be on this test. I think it's 8 because that's SN1. They'll give you different choices here. They'll say, well, which hydrogen is going to be lost? You've got to migrate, or you've got to shift a group so that it forms the more stable carbocation. Secondary to secondary is not valid. You've got to form a more stable carbocation. And certainly going from secondary to primary is not going to be possible. So your choices are maybe going primary, secondary, primary, tertiary, or secondary, tertiary. But if you're moving to the same level of carbocation, you lose. Because it took you energy to shift, you better get something out of that. And if you don't, it's not going to happen. Okay? So that's kind of the rule of shifts. Is you're only one, it's the group next to, it's the carbon next to the carbocation. You can move a methyl or hydrogen, but it's got to give you a more stable carbocation. And if it doesn't, you're not going to have a shift. And I think in today's folder, there was a video on that, and also then the reading for the remainder of the chapter that had carbocations in it. All right. So any questions? I'll take your take-home quizzes. I will release the answer key after this afternoon's class, and then hopefully I'll have them graded by Wednesday. We'll see what happens. But I'll at least have the answer key for you. So if you want, you can put them up here on somewhere there, close to being there. Yeah.
I just want to remind you that I won't be here Friday.